Let's imagine that we have a function on two variables, z equals f of xy. And in the domain of that function, we have this vector function, x of ti plus y of tj, where t is between a and b. So that would give me some kind of curve in the plane. So that's what I'm going to say the graph of r of t is, right? And I could call that a curve. I could think about that as a curve, and I'm going to call that curve c. And so I know that all the xy's on that curve lie in the domain of this function on two variables. And so what I could imagine doing is plugging all of the points on the curve into the function on two variables and getting a z coordinate. Well, this set of parametric equations would give me an x and a y, and so I guess I'm imagining now that I would also get a z, right? And that z would come from this f where I'm plugging in that x and that y. And so for every point on here, I could imagine where the corresponding z coordinate would go, right? So maybe I plug that in point in, and then this function tells me, to plot a point at that height. And so I could imagine doing that kind of for every point. So I'm going to draw a curve in space to represent what happens when I think about plugging in the points on the curve to this vector function. And so I'd get a curve in space. All right, kind of like a roller coaster. Another way to think about this is the function z equals f of xy would give us some kind of surface, and then this purple curve lies on that surface. It's the intersection of the cylinder I would get when I come straight out of the plane over the curve c, and I hit that surface. But I think a nice way to think about it is just this ordered triple, x and y coming from the plane curve, and now the new height coming from the function. And an interesting thing I notice is it's like I have a curved wall, right? I curve along C, and now I have a height. And so I want to talk about finding the area of this curved wall, the portion of the cylinder, if I drug C out, that goes up and hits that surface. Well, I could approach it almost just like we would in a Calc 2. I could imagine partitioning, and I've kind of already done that in a way. Right? The curve itself, I could imagine chopping the curve itself into some number of subintervals, and I could say that the kth subinterval had a length delta s sub k. Right? Using s here because I'm imagining that that curve C would have an arc length, right? So I'm chopping the total arc length up into little bitty pieces. And then on every subinterval, I take a sample point, and I use that sample point, and I plug it into my function to get a height to use as a representation of all of the heights on that subinterval. And in fact, I could imagine that on the kth subinterval, that point is x sub k, y sub k. And so I could approximate the area of that wall by taking all those little areas and adding them together. Well, the height comes from the function value at my sample point times the width delta s sub k. So that sum should approximate the area of that curved wall. All right, so now what do? I want to go from an area approximation to the actual area. Well, I would take a limit as n approaches infinity, or as the lengths of the intervals go down to 0. All right, so this limit, definitely a Riemann sum, right? I have a function times a delta s here. And so this is what we take as the definition of a line integral in the plane. And our notation for that will be this. We have the definite integral over the curve C of f of xy ds, where s is the arc length, or we can actually think about it as the arc length parameter that we defined earlier in the course. This, however, doesn't really make for a evaluation theorem, right? This is a definition, right? And we could actually probably find the limit of these Riemann sums, but it'd be nice to have an evaluation formula for this. And so one of the things we saw earlier in the course was that the derivative of arc length with respect to t, the parameter ds dt, was equal to speed, the magnitude of the velocity vector. So we can rewrite that as a differential relationship. And then this provides us a substitution, that this line integral over the curve C with respect to arc length would be the same as, well, I replace x with the function for x. All of my x's came from that vector function, my y's. And now I go from an integral that was defined on S to an integral that was defined on T, because ds is the same as speed dt. My bounds for T, well, they're from A to B. And so there is my definition of line integral, and here is my calculation formula for the line integral. Every time I want to evaluate a line integral, I actually do this substitution and take an integral from A to B of f of x of t, y of t times speed dt.